Welcome to the deep dive. Today we're tackling something really core to how computers work, process synchronization and deadlocks in operating systems.
hmm
Think of it like maybe preparing for a really critical exam,
hmm
where you need every single detail locked down. That's kind of our approach today.
Exactly. And we're basing this on the materials you, the learner, sent
Mhm.
over. You're clearly aiming for that deep, test-ready grasp of these synchronization issues and, well, those deadlock situations that can really trip things up.
Yeah, they can be tricky.
You've given us some great stuff to work with.
So our mission today is basically to build that perfect mental study guide. We'll break down these concepts, which, let's be honest, can get pretty complex, into clearer pieces, really highlight the key principles for you.
Sounds good. Where should we
Right.
start? Process synchronization itself.
Yeah, let's start there. But maybe first, the difference between processes. Independent versus cooperating.
Good idea. Okay, so an independent process is pretty straightforward. It runs, does its thing, and its execution doesn't mess with any other process. It's kind of in its own little bubble,
Like, maybe different apps running that don't share any data.
pretty much. But cooperating processes, that's where things get interesting. The execution of one can affect others. If one process updates some shared piece of information, another process using that information will see that change.
Right, and that's where the need for synchronization comes in, isn't it?
Precisely. This whole topic, all the problems and solutions we're about to discuss, they really only matter when you have these cooperating processes interacting with shared stuff. That's a key point for your notes.
Okay, so for that exam scenario, how do we define process synchronization itself? What's the core idea?
At its heart, process synchronization is all about managing how these cooperating processes share system resources. It's about controlling concurrent access to shared data so that you don't end up with, well, inconsistent results, maintaining data integrity.
It's like setting up traffic lights for processes trying to use the same intersection, the shared data.
That's a great analogy, actually. Without those rules, those synchronization mechanisms, you can easily get into trouble. The order in which things happen suddenly matters a lot, and it can lead to incorrect outcomes.
Which brings us to race conditions.
The classic problem, yeah.
Yeah.
A race condition happens when you have multiple processes manipulating the same shared data concurrently. And the final result depends entirely on the specific order they happen to run in.
Like they're racing to update the data, and whoever gets there last might determine the final, possibly wrong state.
Exactly. Because the OS can switch between processes at almost any time,
Yeah.
right? So the sequence of reads and writes to that shared data becomes unpredictable. You can't guarantee it.
That unpredictability is the killer.
It really is. Leads to
Yeah.
data corruption, unexpected behavior,
Yeah.
all sorts of headaches.
Can we walk through an example, maybe that producer-consumer one again? That usually makes it clearer for studying.
Absolutely. Perfect example. So you have a producer process creating items, putting them into a shared buffer, and a consumer process taking them out.
And they share that counter variable.
Right. A counter tracks how many items are in the buffer. Producer increments it, consumer decrements it. But here's the catch, and this is vital for understanding race conditions. Counter plus plus or counter, they aren't single atomic operations.
Ah, right. They break down into smaller steps.
Exactly. Counter plus plus usually involves like 3 steps. Load the counter value into a CPU register, increment the value in the register, and then store that new value back into memory where the counter lives. Counter is similar.
And the OS can switch processes between those steps.
Precisely. So let's imagine the counter is 5. The producer reads the value 5 into its register. It increments it to 6 in the register. Now, context switch. Before the producer writes 6 back to memory,
The consumer gets a turn.
right? The consumer reads the counter value from memory. It still sees 5. It decrements it to 4 in its register. Then maybe the producer gets switched back in and writes its 6 to memory. Then the consumer writes its 4.
So the final value is 4, but it should be 5 because 1 was added and 1 was removed.
Exactly. The final count is wrong. Or if the writes happened in the other order, the final value could be 6. Also wrong. It's inconsistent because those multi-step operations got interleaved incorrectly.
That really drives home the data inconsistency problem, and this whole issue leads directly to the critical section problem, doesn't it?
It does. That segment of code where a process is accessing or modifying shared data, that's its critical section.
Danger zone.
Kind of, yeah. And the fundamental rule, the one you absolutely need to know, is when one process is executing in its critical section, related to some specific shared data, no other process can be allowed to execute in its critical section if it accesses the same shared data.
Mutual exclusion, keep them out while one is working in there.
Exactly. So the challenge, the critical section problem, is designing a protocol, a set of rules that processes can follow to cooperate safely.
And this protocol usually involves a few parts for each process.
Typically, yes. There's an entry section where the process requests permission to enter its critical section, then the critical section itself. After that, an exit section where it signals it's done with the shared resource, and finally the remainder section, which is just the rest of its code that doesn't involve that specific shared resource.
Request, enter, do work, signal exit, continue. Seems logical.
It is. And any valid solution to this problem, any good protocol, must meet 3 essential requirements. Definitely jot these down.
Okay, what are they?
First, mutual exclusion. We've basically covered that only one process in the critical section for a given resource at a time. Second, progress. If nobody's in the critical section and some processes want to get in, the decision about who gets in next can't be postponed forever. And only those processes waiting to get in, not those just doing other stuff, should participate in that decision.
Makes sense. No unnecessary blocking.
Right. And third, bounded waiting. There has to be a limit on how many times other processes get to enter their critical sections after a process has made a request to enter its own and before that request is granted.
So no starvation. Everyone eventually gets a turn.
Exactly. Fairness. These 3, mutual exclusion, progress, bounded waiting, are the pillars of a correct critical section solution.
How do operating systems actually handle this? You mentioned preemptive versus non-preemptive kernels earlier.
Right. A non-preemptive kernel is interesting because while it's running kernel code, it can't be interrupted. So within the kernel itself, race conditions on shared kernel data are less of an issue because only one thing is happening at a time.
Ah, okay. But preemptive kernels, which are more common now, can be interrupted.
They can, which means they need explicit mechanisms to protect shared kernel data structures, using techniques like the ones we're discussing.
Got it. Now, one solution mentioned in the materials is Peterson's solution. It's described as the classic software approach.
It is. Peterson's solution is quite clever, designed specifically for 2 processes trying to share something. It uses a couple of shared variables, a Boolean flag array, and an integer turn variable to sort of negotiate who gets into the critical section.
But the notes also say it has issues on modern hardware. Why is that important to understand?
It's crucial because modern processors and compilers often reorder instructions to optimize performance. Peterson's algorithm relies on a very specific sequence of memory reads and writes to work correctly. If the hardware reorders those operations, the logic can break down, and you might lose mutual exclusion.
So it might look right on paper, but the physical reality of the hardware interferes. Why study it then?
Because it's a fantastic algorithmic example. It really illustrates the inherent difficulties in solving the critical section problem using only software logic. It shows you the kind of careful coordination needed, even if the low-level hardware details make this specific solution unreliable in practice today. It's good conceptual groundwork.
Okay, a historical and conceptual stepping stone. And it uses that turn variable to indicate whose turn it is, and the flag array to show who's ready or interested.
That's the basic idea, yes.
Yeah.
Flagging true means process I wants in, and turn decides who gets priority if both want in at the same time.
All right. So if software-only solutions are tricky, what about hardware help?
Hardware support is pretty much essential these days. One older idea for single processor systems was disabling interrupts. If you disable interrupts before entering the critical section, nothing else can run and interfere until you re-enable them.
But that doesn't work well on multiprocessor systems, right?
Not really, no. Disabling interrupts on one CPU doesn't stop another CPU from accessing the same shared memory. It's also generally a blunt instrument. A more common hardware-supported approach is using locks.
Locks. Simple idea. Acquire the lock, enter critical section, release the lock.
Fundamentally, yes. If you try to acquire a lock that's already held, you have to wait. And the key is that acquiring and releasing the lock needs to be atomic.
Which brings us back to atomic instructions.
Exactly. Hardware provides special instructions that are guaranteed to execute as a single, indivisible unit. No interruptions possible mid-instruction.
And the common examples were test and set and compare and swap.
Those are 2 very important ones. Test and set takes a Boolean variable, rlock, maybe initialized to false, sends it to true, and crucially, returns the value it had before it was set.
So if it returns false, you know you were the one who successfully set it to true and grabbed the lock. If it returns true, someone else already had it.
Precisely. Compare and swap is a bit more general. It takes a memory location, an expected current value, and a new value. It atomically checks if the location currently holds the expected value. If yes, it updates the location with the new value and returns the original value. If no, it does nothing and returns the original non-matching value.
So you could try to swap a lock variable from 0 unlocked to 1 locked, expecting it to be 0. If the swap succeeds, you got the lock.
Exactly. The atomicity provided by the hardware is the foundation upon which we build reliable locking mechanisms. Your materials also briefly mention a more complex test stand set-based solution that satisfies bounded weighting using a shared weighting array.
Yes, I saw that. Now, these atomic instructions let us build things like mutex locks, right? Which
Yeah,
are widely used.
that's right. Mutex locks, or mutual exclusion locks, are a common software abstraction built using these atomic hardware primitives. They provide that acquire and release interface to protect critical sections.
So acquire tries to get the lock, maybe using test stand set or compare and swap.
Often, yes. And if the lock isn't available, the simplest implementation of acquire might just loop, constantly checking the lock again and again. This is called busy waiting or a spin lock.
And release just sets the lock back to available.
Atomically, yes. But that busy waiting, it can waste a lot of CPU time if the lock is held for a while. The processor's just spinning, doing no useful work.
Which is the problem that semaphores were designed to address.
Exactly. Semaphores offer a way to handle waiting without wasting CPU cycles in busy loops. A semaphore is essentially an integer variable. Let's call it S.
And you only access it through two special atomic operations, wait and signal.
Correct. Sometimes wait is called P in signal. It's called V from the original Dutch terms.
Okay, so what does wait S do?
The basic idea of wait S is it checks the semaphore value S. If S is positive, it decrements S by 1, and the process continues into its critical section. If S is 0 or negative, the process blocks. It stops running and waits.
And signal S?
Signal S by 1. If there are any processes blocked waiting on S, the signal operation typically wakes one of them up, allowing it to potentially complete its wait operation and proceed.
So wait before the critical section, signal after. And the blocking avoids busy waiting.
That's the core concept. And crucially, like the mutex operations, wait and signal on the same semaphore must themselves be atomic operations. You can't have two processes modifying the semaphore value simultaneously.
We also saw two types, counting and binary semaphores.
Right. A counting semaphore can have any non-negative integer value. It's often used to manage a resource with multiple identical instances. You initialize it to the number of available resources, say k. Each wait consumes a resource, decrements the count. Each signal releases one, increments it. If the count hits 0, subsequent wait calls block until someone signals.
Like managing licenses for software or connections in a pool.
Exactly. A binary semaphore, on the other hand, can only be 0 or 1. It basically acts like a mutex lock, used for simple mutual exclusion around a single resource or critical section.
And you mentioned they could also be used for synchronization between processes, like making one wait for another.
Yes. If you initialize a binary semaphore cinch to 0, process P1 does some work, S1, and then calls signal cinch. Process P2, before doing its dependent work, S2, calls wait cinch. P2 will block at the wait until P1 finishes S1 and signals, ensuring S1 happens before S2.
Clever. Now, how do we implement these wait and signal operations without busy waiting? The notes had more detail there.
Okay, so instead of spinning when wait finds S is not positive, the process adds itself to a waiting queue associated with semaphore S, and then calls a scheduler function, say block, which suspends the process. The CPU is then free to run other processes.
It puts itself to sleep, essentially. How does it wake up?
When another process executes signal S, it increments S. If S is still 0 or negative, meaning processes are waiting, it removes one process, say P, from the waiting queue for S and calls wake up P. This moves process P from the waiting state to the ready state, putting it back in the ready queue so the scheduler can run it later.
And the semaphore structure itself needs to store not just the integer value, but also that list or queue of waiting processes.
Correct. Usually it's a struct containing the integer value and a pointer list to the queue. And in this implementation, the value can actually become negative. If value is negative, its absolute value tells you how many processes are currently blocked on that semaphore's queue.
That's a useful detail. And ensuring atomicity for these wait and signal implementations still need that?
Yes. On a single CPU, you can briefly disable interrupts while modifying the semaphore value in queue. On multi-CPU systems, you typically protect these short critical sections within wait and signal using spin locks. Since the operations are very fast, minimizing the busy waiting time.
Okay, semaphores seem very versatile,
Yeah,
but they aren't a silver bullet, right? Deadlocks can still happen.
absolutely. Even with waiting queues, you can get into deadlock situations. Imagine two processes, P0 and P1, and two semaphores, S and Q, both initialized to 1.
Okay.
P0 does wait S, then P1 does wait Q. Now, P0 needs Q, so it does wait Q, but P1 holds Q. P1 needs S, so it does wait S. But P0 holds S.
They're stuck, each waiting for the resource the other one holds. Classic deadlock.
Exactly. And there's also the risk of starvation, where a process keeps getting unlucky and never gets woken up from the semaphore queue, even if the resource becomes available multiple times.
Right. These issues lead us to look at those classical synchronization problems, which are great test cases for these tools. First, the bounded buffer problem again, but solved with semaphores.
Okay. We need to manage access to the shared buffer, size M, prevent overflow underflow, and prevent race conditions when accessing the buffer itself.
And the solution uses 3 semaphores.
Typically, yes. Mutex, a binary semaphore initialized to 1 for exclusive access to manipulate the buffer. Empty, a counting semaphore initialized to N, tracking empty slots. And full, a counting semaphore initialized to 0, tracking filled slots.
So the producer has to wait empty before adding, and the consumer has to wait full before removing.
Correct, and both need to wait mutex before actually touching the buffer structure and signal mutex immediately after. The producer also signals full after adding, and the consumer signals empty after removing.
That seems to cover all the bases, buffer limits, and mutual access.
It's a very standard and elegant solution using semaphores.
Next up, the dining philosophers. Always a fun one.
It is. 5 philosophers, circular table, 5 chopsticks, 1 between each pair. Need 2 adjacent chopsticks to eat. Alternate thinking and eating.
And the deadlock happens if they all grab their left chopstick simultaneously.
Precisely. If we model each chopstick as a binary semaphore initialized to 1, and each philosopher does wait, left chopstick, then wait, right chopstick, they can all get stuck holding one, waiting for the other. All semaphore values become 0. Gridlock.
How do we fix it? The notes had a few ideas.
Several ways. You could limit the number of philosophers allowed at the table, say only 4, so at least one chopstick is always free. Or a philosopher must be able to pick up both chopsticks simultaneously, atomically in a sense, or pick up neither. Another common fix is an asymmetric approach. Odd philosophers pick left then right, even philosophers pick right then left. This breaks the circular dependency.
Those all prevent the everyone grabs left scenario. Okay, last classical one, readers, writers.
Right. Shared data. Readers just read. Writers read and write. Multiple readers are okay concurrently, but a writer needs exclusive access. No other readers or writers allowed while a writer is active.
So, prioritize concurrent reads, but ensure writer exclusivity. How's that usually handled with semaphores?
You typically use a semaphore or a mutex, initialized to 1, that writers must acquire before writing and release after. Readers also use this, but in a more nuanced way. You also need another semaphore, mutex, initialized to 1, to protect a shared integer read count, initialized to 0.
Okay, read count tracks active readers. How do readers use these?
A reader first does wait mutex to get exclusive access to read count. It increments read count. Now, if this reader's the first one, read count just became 1. It also does wait and mutex. This locks out any writers. Then the reader releases the lock on the counter by doing signal mutex. Now it can read the data.
So the first reader locks out writers, subsequent readers just increment the count. What happens when they finish?
When a reader finishes, it does wait mutex again, decrements read count. If read count is now 0, meaning this is the last active reader, it signals the writer lock. Signal mutex. This allows the waiting writer, if any, to proceed. Finally, the reader releases the counterlock. Signal mutex.
Wow, okay, that's more intricate. The first reader acts as a gatekeeper against writers, and the last reader opens the gate again.
It's a common pattern, though variations exist that might prioritize writers differently or prevent reader starvation.
All right, that covers the classical problems. The last synchronization tool in the material is monitors. How are they different?
Monitors are a higher-level abstraction. Think of a monitor as a programming language construct, like a special kind of class or module. It bundles shared data together with the procedures that operate on that data.
And the key feature.
Automatic mutual exclusion. The monitor guarantees that only one process can be executing any procedure within that monitor at any given time. If a process calls a monitor procedure and another process is already active inside, the calling process is automatically blocked and placed in an entry queue.
So the compiler or runtime system handles the locking and unlocking implicitly.
Essentially, yes. It simplifies concurrent programming because you don't have to manage mutexes explicitly for accessing the monitor's shared data through its procedures. You just call it procedures.
But sometimes a process inside the monitor needs to wait for something specific within the monitor.
Right. The basic mutual exclusion isn't always enough. That's where condition variables come in. Inside a monitor, you can declare condition variables, say condition X.
And they have wait and signal operations too.
Yes, but they work differently than semaphore wait signal. If a process inside the monitor calls x.wait, it releases the monitor lock, allowing the other process to enter, and goes to sleep on a queue associated specifically with condition X.
It yields control while waiting for that condition.
Exactly. When another process, also inside the monitor, determines that the condition X might now be true, it can call x.signal. This wakes up exactly one process waiting on condition X.
Just one. Okay, what happens then? Who gets the monitor lock?
That depends on the monitor's semantics. Two main styles. Signal and wait means the signaler pauses and the awakened process runs immediately, getting the monitor lock. When the awakened process eventually leaves the monitor or waits again, the original signaler might resume. Signal and continue means the signaler keeps the monitor lock and continues running, while the awakened process has to wait to reacquire the monitor lock when the signaler eventually releases it.
Different ways to manage the handoff. And the dining philosophers can be solved with monitors too.
Yes. You define a dining philosopher's monitor. Inside, you'd have the state array, thinking, hungry, eating, and an array of condition variables, self of 5, one per philosopher. A philosopher, I could only set state I to eating if neighbors aren't eating. Procedures like pickup would check neighbors. If unable to eat, the philosopher calls selfie.wait. Put down would change state back to thinking and then check neighbors, potentially calling signal on a neighbor's condition variable if they were waiting and can now eat.
So the monitor handles the mutual exclusion for checking changing states, and condition variables handle the waiting notification for chopsticks.
Exactly. It often leads to cleaner looking code than semaphore solutions for complex synchronization.
Okay, that's a really solid overview of synchronization. Now, let's shift gears to the other major topic, deadlocks. The ultimate standstill.
Right, where progress just stops because processes are stuck waiting for each other. In a multi-programming system, it's a set of blocked processes, each holding some resource and waiting to acquire a resource held by another process in the set.
A circular wait for resources. And we noted earlier that some major OCs, like Windows and Linux, often just ignore the problem. How does that work in practice?
Well, it's a pragmatic choice. They operate on the assumption that true deadlocks are rare enough in typical workloads that the performance overhead of constantly preventing or detecting them isn't worth it. If a deadlock does happen, the solution might just be a reboot or killing the affected processes, like a cost-benefit analysis.
Risking an occasional hang versus slowing things down all the time.
Pretty much. But understanding deadlock principles is still vital, even if an OS doesn't explicitly implement avoidance or detection.
That simple analogy helps. Process A has resource R1, needs R2. Process B has R2, needs R1. Boom. Deadlock.
Can't get simpler than that. And it's not just hardware resources like printers or drives. It could be software locks, database records, anything requiring exclusive access.
Let's nail down resource again. Anything used by one process at a time.
Essentially, hardware device, piece of information, lock, etc. And remember, resources can have single instances, like maybe a specific tape drive, or multiple identical instances, like CPU cores or memory pages.
And that difference between preemptible and non-preemptible resources is key for deadlocks, right?
Absolutely. A preemptible resource, like RAM, can usually be taken away from a process, given to another, and then returned later without causing failure. A non-preemptible resource, like a printer mid-job or a file lock, cannot be taken away. The process must release it voluntarily. Deadlocks primarily involve non-preemptible resources.
Because if you could just take the resource away, preempt it, you could break the deadlock cycle.
Exactly. The typical resource usage pattern is request, use, release. Deadlocks happen when requests block indefinitely within that cycle.
Okay, crucial for the exam prep. The 4 necessary conditions for deadlock. What are they again? All must hold simultaneously?
Right. The Kaufman conditions. First, mutual exclusion. At least one resource involved must be non-shareable. Only one process can use it at a time.
Makes sense.
Second, hold and wait. A process must be holding at least one resource while waiting to acquire additional resources held by other processes.
Holding something, waiting for something else.
Okay. Third, no preemption. Resources can only be released voluntarily by the process holding them after it's finished. They can't be forcibly taken away.
Got it.
And fourth, Circular wait. There must be a chain of processes, P0, P1.Pn, where PO is waiting for a resource held by P1, P1 is waiting for one held by P2, and so on, until Pn is waiting for a resource held by P0.
The snake eating its own tail. And all four must be true at the same instant.
Yes. If you can prevent even one of these conditions from ever holding true, you can prevent deadlocks entirely. That's the basis of deadlock prevention strategies.
Before we get to prevention, what about that resource allocation graph? How does that help visualize things?
It's a directed graph. You have nodes for processes, circles, and nodes for resource types, rectangles. Dots inside a rectangle show multiple instances of that resource type.
And the edges show.
Two kinds. A request edge goes from a process pi to a resource type RJ, pi, RJ, meaning pi wants an instance of RJ and is waiting. An assignment edge goes from a resource instance, a dot inside RJ, to a process pi, RJR, meaning that instance is currently allocated to pi.
So you can trace who has what and who wants what. How does it show deadlocks?
Cycles are the key. If there are no cycles in the graph, there's no deadlock. If there is a cycle, no, well, it depends.
That single versus multiple instance distinction again.
Exactly. If every resource type in the cycle has only one instance, then a cycle guarantees a deadlock. The processes in the cycle are stuck. But if there are multiple instances of resources within the cycle, a cycle is necessary but not sufficient. A deadlock might exist, but it's also possible that processes could eventually get the resources they need from other instances not involved in the immediate cycle.
Okay, that's a subtle but important point. So, dealing with deadlocks, we mentioned ignoring them. What are the proactive strategies?
Two main families, deadlock prevention and deadlock avoidance. And then there's deadlock detection and recovery.
Let's start with prevention, breaking one of the four conditions.
Right. To break mutual exclusion is often impossible. Some resources just are non-shareable. To break hold and wait, you could require processes to request all needed resources at the very beginning. If they can't get everything, they get nothing and wait. But this can be inefficient, holding resources longer than needed.
Low utilization. What about no preemption?
You could allow preemption. If a process holding resources requests another it can't get, it might be forced to release what it holds. Or if a process requests resources held by a waiting process, the waiting process might be preempted. This is complex and not always feasible.
And circular wait.
A common prevention technique here is to impose a total ordering on all resource types. Every process must request resources in strictly increasing order according to this numbering. This makes a circular wait impossible.
So prevention imposes strict rules up front to make deadlocks impossible. What about avoidance? It sounded more dynamic.
It is. Deadlock avoidance requires the OS to have some extra information up front, usually the maximum number of each resource type a process might ever need. Then, for each resource request, the system checks if granting that request could potentially lead to a deadlock down the line.
How does it check? Using the safe state idea.
Exactly. A state is safe if there's some sequence in which all current processes can finish executing, even if they all request their maximum resources. An unsafe state is one where no such guarantee exists. Deadlock avoidance algorithms ensure the system never enters an unsafe state.
So, even if a resource is technically free right now, the OS might make a process wait if granting the request would move the system from a safe state to an unsafe one.
Precisely. It's playing it safe, looking ahead based on those maximum resource claims.
And the two algorithms here were the resource allocation graph algorithm for single instances and Banker's algorithm for multiple instances.
Yes, the graph algorithm for single instances introduces claim edges, dashed lines, showing potential future requests. A request is only granted if converting the request edge to an assignment edge doesn't create a cycle, checked using cycle detection.
It checks for immediate cycle creation upon allocation. And Banker's.
Banker's algorithm is more complex. It maintains tables of maximum needs, current allocations, and available resources. When a request comes in, it pretends to grant it, then runs a safety algorithm to see if a safe sequence still exists in this hypothetical new state. If yes, the request is actually granted. If no, the process waits.
Feels like it needs quite a bit of bookkeeping and upfront information, the max needs.
It does, which is why it's not always practical, but it's the classic avoidance algorithm. The core idea is always staying in a safe state.
Okay. But what if we don't prevent or avoid? What if we let deadlocks happen and then deal with them? That's detection and recovery.
Right. First step is detection, realizing a deadlock has occurred. Again, the algorithm depends on resource instances.
Single instance based.
For single instances, you use a wait for graph. It's like the resource allocation graph, but only shows processes. An edge pi, PJ, means pi is waiting for a resource held by PJ. A deadlock exists if and only if there's a cycle in the wait for graph. The OS periodically builds this graph and checks for cycles.
Simple enough, multiple instances.
More complex. It uses similar data structures to the banker's algorithm, available, allocation, request matrices. It periodically runs an algorithm that tries to see if there's an order in which processes can finish given the current state. If some processes cannot be placed in such an order, they are deemed deadlocked.
Your notes had an example showing it could pinpoint exactly which processes were involved in the deadlock.
Yes, the detection algorithm can identify the set of deadlocked processes.
Okay, so we've detected a deadlock. Now what? Recovery.
Two main options: process termination or resource preemption.
Process termination sounds drastic.
It can be. Option 1, kill all the processes involved in the deadlock. Simple, but you lose a lot of computation. Option 2, kill them one by one, running the detection algorithm after each kill until the cycle is broken.
How do you choose which one to kill?
That's the tricky part. You might consider process priority, how long it's been running, how many resources it holds, how many more it needs, maybe just how many processes you need to kill in total. It's often based on minimizing cost or impact.
Seems messy. What about resource preemption? Taking resources away.
Also complex. You need to decide which resources to preempt from which victim process. Again, you want to minimize cost. But then you have the issue of rollback. What state do you put the preempted process back into? Often it means aborting and restarting it anyway.
So it might still lead to termination, effectively.
It often does.
Yeah.
And you also have the starvation issue you need to ensure the same process isn't always chosen as the victim for preemption. Maybe track how many times each process has been preempted.
So recovery is definitely not trivial either way.
Not at all. It highlights why prevention or avoidance are often preferred if the overhead is acceptable and the conditions can be met.
Wow. Okay, that was a very comprehensive tour through synchronization and deadlocks. We went from race conditions and critical sections through mutexes, semaphores, monitors, all the way to deadlock conditions, avoidance, detection, recovery. It's a lot to absorb.
It definitely is. But these concepts are really fundamental to how operating systems manage complexity and concurrency. Understanding this is like understanding the engine under the hood. Crucial if you want to grasp how the whole system performs reliably. Getting these down is key exam prep.
Absolutely. So, for you, the learner, and everyone listening, here's something to think about, building on all this. We talked about the trade-offs between deadlock prevention, avoidance, and detection recovery. Can you think of specific types of systems, maybe real-time systems or databases or general-purpose desktops, where one approach might be clearly better or even required compared to the others? What factors would make you choose one strategy over the others in a particular context?
That's a great question to mull over. It forces you to apply these concepts to different scenarios.
Definitely something to consider. Well, that wraps up our deep dive for today. Thanks for joining us.